Dr. Shruthi is a distinguished structural biologist at NCBS specializing in understanding cellular protein organization. Her research focuses on unraveling the structural patterns of protein complexes, macromolecular assemblies, and nanoscale architectures, providing invaluable insights into cellular processes and molecular machinery. Collaborations with fellow biologists enrich her research, and she pioneers computational modeling methods to enhance accuracy and efficiency in protein structure determination. Dr. Shruti Akka, please let us know more about Biobytes Young Minds on AI Adventures.
Dr. Shaon Chakrabarti addresses a central challenge in cell biology: comprehending and quantitatively predicting population growth resulting from heterogeneous single cell division kinetics. This research is crucial for unraveling how cells respond to drugs, especially in diseases like cancer. Dr. Shawn Anna's lab employs various live and fixed cell imaging techniques in experiments and utilize methods from statistical physics, stochastic modeling, biostatistics, and machine learning in their theoretical work. Shawn Anna, we're eagerly waiting to hear more about Biobytes, young minds on an AI adventure.
So now we go to module 2. You know something about what AI and ML is, and what can it do? It can recognize simple shapes like distinguishing these triangles from these circles to doing more complex things like identifying whether that's a cheetah or a leopard and identifying whether given this image is it a puppy or a cupcake, to doing even more complex things like driving cars and generating paintings, generating art. So how does it do all of this? The answer is interesting. In fact, it is just a larger version of what Shaon was describing. He was describing this method, this computer algorithm that takes some data and then finds the best fit to a line. And AI is doing all of this using something very similar called a neural network, which is just a larger version with more parameters, more equations, thousands of equations, and basically a larger version of this. And it is inspired by how the human brain works. So we'll listen to a video where we see how this works.
Hi, I'm Dion. I'm one of the creators of Forethought AI. At Forethought, we build artificially intelligent tools that people can use at work to be more productive. To make a learning machine, early computer scientists looked for clues by studying other things that are good at learning. And it turns out that nothing is better at learning than the human brain. Our brains are made up of special cells called neurons. A neuron has two ends. Input signals enter in on one end, they're combined together inside the neuron, and leave the other end as a single output. All of the billions of neurons in your brain are connected to each other in what's called a biological neural network. It's how your brain processes information and recognizes patterns. Early AI scientists decided to mimic human neurons by making their own simple artificial neurons in software. Nothing fancy, just multiple signals going in as inputs, passing through the neuron, and getting combined and processed by some simple math into a new signal going out. And it's a good start. But one neuron alone doesn't do much. The full potential of this idea is only unleashed when the artificial neurons are connected together to make an artificial neural network. This is what allows computers to recognize images, drive cars, and make some truly weird art. To see how a neuron works, let's build a movie recommendation system that uses critics' reviews to guess how much you'll like a movie. Then we'll use your feedback to make the system better. Here are 3 movie critics, Ali, Bowie, and Casey. Each one rates a movie anywhere from 1 to 5 stars. Now let's build a single artificial neuron. Each of the critics' ratings enters on this side as input. Some calculations are done in here, and we get a single output. In this case, it's a movie rating. Here's the first movie. Ali gives it 1 star, Bowie gives it 5, and Casey gives it a 4-star review. At first, the critics' opinions all carry the same weight and are counted equally. The inputs enter, there's some basic math, and out comes a recommendation. Now, let's watch the movie so we can give it our own rating. Okay, that was weird. Let's pretend you really liked it and gave it a 5-star rating. The rating you just provided is now used to train the neuron. Based on your rating, the weight of each critic's opinion is recalculated. Your rating is closer to that of Bowie and Casey, so their opinions get more weight. You didn't agree with Ali's single-star review, so that weight goes down. Now let's train the neuron again. Here's another movie, and here are new ratings from our critics. And this time, the neuron will give more weight to these 2 ratings when calculating its recommendation. And here's the output. Now let's give it a watch. Well, at least that was short. Let's give it a rating. Our new rating adjusts the weights again. This process repeats over and over until we've trained the system to know our preferences and recommend movies that we'll probably enjoy. In this example, there's just one neuron. That's far more simplistic than most systems. Powerful neural networks have millions of neurons arranged in layers. There are input layers, any number of hidden layers, and output layers. The output of one layer of neurons becomes the input to the next layer, and so on. Many real-world media, music, and shopping recommendation systems work like this, using ratings from millions of everyday users. In those neural networks, everyone has a hand in modifying the weights. Neural networks have so many other uses. They're working behind the scenes on big problems like growing healthier food, predicting floods and forest fires, aiding wildlife conservation, and even detecting and curing disease.
Okay. Do we have any questions? If not, Karthik will lead you through an activity that uses neural networks. Karthik?
Hello. Hello there. Okay. Just open the door. Just a link. Okay, guys. So, now as Shaon told you guys that AI is not just some black magic or something, but rather math behind. And you saw in this video how a neural network is actually made to learn from the data that you're given. So, here we'll do a small activity as to show you with a simple online tutorial kind of say to how a model is actually trained. So, in this case, there are 3 tasks in which we'll be training a neural network to perform one of those tasks. You can choose which one we want to perform. Like over here we have an image project which will basically classify the input image into whether it's, say, a cat or dog, or say, a boy versus a girl. or say an audio project wherein the model will be trained to recognize difference between two, say, songs, or a pose project wherein it can be trained to differentiate between two different poses. So guys, which one would you like to do? Pose.
How many for pose?
How many for pose? Okay, hands down. How many for audio? Good. And how many for the? Okay, I guess that's still fine. So now I need some volunteers for the audio project. Who's ready to come and sing a song?
Anyone from here?
Anyone who wanted to do the audio project? It need not even be a song. It could be anything. It would just be some random sentences that you say. Just introduce yourself. That's also fine. It need not be a song exactly. Come. Could be anything, not just a song or just anything, whatever you want.
Line. Real.
Come on, come on. If you're not coming, then Shruthi and Shaon will have to do.
Classifier singing and back. Krishna is here and she'll sing a song for us.
So will come. Okay, so over here, see, basically this is what's called a binary classifier. Binary classifier basically is a model which is classifying one of the two classes. There are two classes. Over here, there will be what you will put as a background noise class, which will be not just the background noise in the room. And then the second class, which can be the song which she will be singing. Right? So first, and yeah, the model will learn on some data. So basically, this background noise and the song that she's gonna sing will be our data on which the model will be trained. Right? So first thing over here, you just put some background noise. Okay, so nobody needs to say anything.
Go.
That will do. That one.
Now we'll sing.
As long as you want.
ಲೋಕದ ಕಣ್ಣಿಗೆ ರಾಧೆಯು ಕೂಡ ಎಲ್ಲರಂತೆ ಒಂದು ಹೆಣ್ಣು ನನಗೂ ಆಕೆ ಕೃಷ್ಣನ ತೋರುವ ಪ್ರೀತಿಯು ನೀಡಿದ ಕಣ್ಣು.
Good. So now we have a background noise class, which you guys were clapping and doing all sorts of things. Good. And then we have a song class in which basically we have a song being sung. Right. So now we want to train our model for this. we need more of the noise class.
My name is Samuel. I'm gonna be song by Imagine Dragons.
Anyways, if there's anyone else who still wants to volunteer, we still have another part left. Well, we have the data for background noise, a song, and how cuckoo sings, how a human sings, and how cuckoo sings. So now, let's train the model. So when you click on train model, basically, based on the data that you have just collected over here, this particular neural network model will be trained. Cool. Will it be too loud now? It's fine? Cool. So just to tell, for this particular neural network, these guys use what's called a mobile net neural network architecture, which is a lightweight deep neural network, right? And it seems the model has been trained now. So now, who wants to volunteer? Come. We need another cuckoo, a human singer, and I guess all of you can contribute to background noise.
Way down south in the land of traders. Yeah, that's pretty.
The first thing to see is how probable is the particular input that you have made belonging to one of the particular clouds. We have background noise, the human singer, and that's fine. So, start.
Away down south in the land of traders, rattlesnakes and alligators. Right away, right away, right away, right away, right away, right away, right away.
Background noise, or it's actually human singer? Okay, fine. Another cuckoo. to actually, so this is basically how you train a neural network with some given data, right? And then use that model for whatever downstream application you want to use. In this case, we built a classifier to distinguish between 3 different kinds of sound. Cool?
Okay.
Good.
Thank you, Karthik. That was fun. We looked at how computers can learn patterns in voices. Now, we'll play a bit with images. We'll look at how computers see, how they process images, and how they learn patterns. So first, we'll look at a small video.
Hi, my name is Alejandro Carrillo, and I'm a robotics engineer at an agricultural company. Specifically, my team uses machine learning and robotics and computer vision to identify the difference between the crops that we eat and weeds that take nutrients away. And we're able to remove those weeds without any chemicals.
My name is Kate Park, and I work at Tesla Autopilot. I build self-driving cars. Any place where there can be resources used more efficiently, I think is a place where technology can play a role. But of course, one of the best impactful ways of AI, I hope, is through self-driving cars. Have you ever wondered how a computer can recognize a face or drive a car? Or maybe you've wondered why it's so hard for a computer to tell the difference between a dog and a bagel? Well, it all has to do with something called computer vision, the way machines interpret images. Let's take a look at a simple example of how computers learn to see.
Here are two shapes, an X and an O. At some point, you've learned the names for these shapes, but a computer looking at these images for the first time just sees a bunch of little squares called pixels. Each pixel has a numerical value. For a computer to see, it needs to make sense of these numbers to figure out what is in the picture. In traditional programming, you could tell the computer to check which pixels are filled to decide what shape it sees. If the center and corner pixels are full, then it's an X. If the center and corner pixels are empty, then it's an O. Traditional programming works great for this kind of thing. But what about asking the computer to recognize these images? What might the computer think these are? We gave the computer a strict definition of what an X looks like. But these images don't fill all the necessary pixels to fit the definition. So if the computer doesn't think these are X's at all. In fact, the computer thinks these are O's because the corners and center pixels are blank. And that fits the definition of an O that we gave it.
In this example, traditional programming only works some of the time. But with machine learning, we can teach the computer how to recognize shapes no matter their size, symmetry, or rotation. Teaching a computer requires thousands or even millions of examples of training data and a whole lot of trial and error. So let's start training. Here are some simple shapes we can use to train the computer to see. At first, the computer is completely clueless and makes a totally random guess from a preset group of options. And it guesses wrong. But that's okay, because this is where the computer learns. After it makes a guess, the computer is shown the correct answer. It's like learning with flashcards. Sometimes you have to get it wrong before you get it right.
With every guess, the computer looks at each pixel and the surrounding pixels. It tries to recognize patterns and make rules to help it guess. Like if it sees a row of orange pixels next to a row of white pixels, there's an edge. If the computer sees two edges oriented a certain way, say a 90-degree angle, then it's likely to guess that it's looking at a square. It won't get it right every time, But with more trial and error, it will slowly build a more confident guessing algorithm.
Whether it's trying to guess shapes, animals, or any other category, machine learning finds patterns by learning from its mistakes. The training data is used to make a statistical model, which is just a fancy way of saying a guessing machine. When we give it training data, the guessing machine is tuned and optimized to recognize the pictures we gave it, with the hope that it will then be able to recognize new pictures with the same accuracy.
It may seem easy to tell the difference between an X and an O, or to even categorize basic shapes, but most images aren't that simple. Let's take a look at how computer vision can learn to recognize complex images, or scenes like ones in the real world. Most complex images can be broken down into small, simple patterns. For example, an eye is made up of two arcs and some circles inside. A wheel is made up of concentric circles and some radial lines. The way a computer recognizes the patterns in all these pixels by using a neural network made of many layers. The first layer of neurons takes pixel values as numerical inputs to identify edges. The next few layers of neurons take those edges and try to detect simple shapes, until finally the computer puts it all together and understands.
It can take hundreds of thousands or even millions of labeled images to train a computer vision system. But sometimes even that's not enough. Some face recognition systems have trouble even seeing people of color because the system was primarily trained with photos of white people. Sometimes problems in computer vision are silly, like when a computer gets confused trying to tell the difference between these dogs. Oh wait, that's not a dog. But it does kind of look like a dog. At least this dog.
But as society relies on computer vision for real problems, like detecting diseases in medical imagery or helping a self-driving car identify pedestrians, it becomes increasingly important that we all understand how these systems work and what types of problems they're appropriate for.
Computer vision can open up a miraculous world of possibilities, but a machine is ultimately only as good as the data used to train it.
So we looked a little bit about how computers can recognize patterns in images, but computers can do something even more. Computers can actually generate art themselves. So we'll look at a short video about how they can make this step from just predicting things that they've already seen to creating new things. And after this, we'll have an activity on images.
Venezuela, CEO and hi, I'm Cristóbal Valenzuela, CEO and co-founder of Runway, a company creating AI tools for video generation and storytelling. One of our most recent AI tools is an algorithm called Gen 2 that allows you to turn text, just language, into video.
I'm Mira Murati. I'm the Chief Technology Officer at OpenAI, the company that created ChatGPT. Computers were first invented to do math and solve hard problems. And despite all the advances in computer science, most people assume that computers can never have creativity and imagination. But is that still true?
AI systems can not only write stories, they can create images that no one has ever seen before. AI is able to create award-winning art like this.
It can create social media influencers that don't exist in real life.
And even create complete video sequences with just a few words of instruction.
But how does this AI work? And does it have true creativity and imagination? Let's dig in.
Early projects that taught AI to create art used something called a generative adversarial neural network, which is a way of using two AI models to generate images. The way this works is that one AI, called a generator, is trying to create images that are similar to the ones in the training set. And a different adversarial AI trains to detect if those images are close to the originals or not. Both AIs train against each other until the adversarial can no longer detect what image is real and what image was created artificially. At this point, the generative AI has learned to generate real-looking imagery.
Now, this is great, but computer scientists have come up with something even better called diffusion. Inspired by physics, diffusion involves converting an image to an unrecognizable blur or noise and training an AI to reverse this process. Take, for example, this image with all of its detail. We can introduce a little bit of randomness or noise to these pixels, which takes away some of the detail. If you repeat this gradually, 1,000 times, the image loses all details and becomes pure noise. Now, every step of this gradual transition is an opportunity to train AI to learn to reverse the process. An AI neural network can train by looking at the noisy image and then try to generate the slightly less noisy version. Because the noisy version of the image doesn't have all the details, the AI is learning to guess what the higher resolution details should be. And that's how it creates new images.
Now, to train an AI, we repeat this with millions and millions of images, each of them labeled with their descriptions. If we do this enough times, the AI learns to take a text description and generate completely new images nobody has ever seen before, or to alter existing images. The same approach can also be used for videos. Now, this raises multiple questions. Is the AI really learning creativity and imagination? On the one hand, if you look at art and video created by AI, it can be beautiful, original, and amazing. On the other hand, the AI only learns this by doing math at the pixel level, while studying creations made by people. Is that really creativity?
Another question is the issue of copyright. AI learns by studying the creations of others, and the original creators may want to save this. Of course, when humans learn to create, they also study creations made by others. So the legal questions here are not simple.
We're still in the very early days of teaching AI how to create new types of media.
Okay, we'll stop here because we're running a bit late and we'll start the activity. Any questions before we do that? Okay.
How does the artificial intelligence make neuron cell by its own?
Make a neuron cell by its own. Each neuron is essentially a set of equations. That's what we call an artificial neuron. So that's how by combining data from, let's say, many different images and looking at many different equations, it's coming up with a prediction. So that's what an artificial neuron is. It's just a set of equations.
And what is algorithm?
It's the computer method. Like you remember in the first example that Shaon had, you had y is equal to mx plus c. And looking at the data, you had to guess values for m and c. The method to do that is the algorithm. Okay, let's go to the activity. We can take more questions later. Shreyas will guide us through this activity and we need volunteers here as well.
So Shruti showed you that in the video you saw that you can make different art forms. So they also showed a few examples. Now these examples can on one hand be completely randomly generated images, or you can tell the model what you want to generate from these, basically you want the model to generate. So here maybe you cannot see, but even the background is generated by AI. So now what we can try to do here is give it a prompt. A prompt is essentially you telling the system what you want to make. It could be something like a retro gas station on Mars, and we'll build something that matches your prompt. So let's try some simple prompts, right? Any ideas?
Yeah.
Okay. Astronaut in Hogwarts.
What?
Let's try both of those.
Man eating a hot dog on a horse on Mars.
On a horse.
We're almost there, I guess. Okay, what was the other suggestion?
One more. Take it from there.
Astronaut in Hogwarts.
Not bad, right?
Now it's more like it, right? Yeah.
Walking on the board.
So it's a little complex.
A computer in a computer in a computer.
So now what essentially is happening here is there are two networks again. There is first network that sort of learns what you're telling it to do. So you're essentially giving it a prompt, which is then converted into some sort of a representation, which will again be a whole bunch of numbers that the computer can understand. And based on those numbers, your second network will come up with the image.
Okay, we are running short of time. Maybe 2 more prompts and we'll move on. Someone at the back.
An ant carrying an elephant on the bridge on top of a volcano. Here's your computer in a computer in a computer.
Sir,
Yeah, here's your computer.
Can we get the ant one?
Yeah.
An ant carrying an elephant
Carrying
On a volcano.
and carrying an elephant on a bridge on a volcano, on top of a volcano.
On a bridge on a volcano. On top of a volcano. Okay.
Where's that? There is a volcano in the corner, there is an elephant, I don't see the ant.
Ant's too small.
A computer, the Starry Night painting, but using only snakes.
Starry night.
Starry Night painting using snakes.
That's the last one we are going to.
Yeah, that's the last one. We'll have more fun in the end if we have time.
There are
Move on with other things we have to do. Okay, we ran out of
Please,
credit.
there's this one last week. Take this one. We are running out of time.
We are out of credit, so we'll have to do it with another website. So we'll stop here actually. Thanks, players. Thanks, volunteers. Okay, now we'll do something different. We'll play with text. And now I'm not going to introduce. We have others.
Hello? Bacha, are you done with the assignment?
No man, I'm still figuring out this problem here.
Ah, you can't help me.
Hey, if you find the answer, just tell me. No?
Yeah. God, can't you just help me once?
Rocky bhai.
God, are you really here?
my child. I'm not God. Genie. But do you want to know who am I? No. Or you want to solve your problems? Genie.
I don't care who you are. Can you solve my problem?
Selfish humans. How can I assist you?
Please explain me the sedimentation process.
Okay. Sedimentation. So it's a process where the solid particle in a liquid or a gas settle down. Normally we use this process in water purification where the impurities are settled down under the influence of the gravity.
Wow, you made it so easy.
Thank you.
But who are you? Like you said ChatGPT 42, but I don't know what that is. And why are you helping me out for free?
Who am I? I am a part of the great GPT family. I am a deep neural network, a language model. I am a great transformer architect.
Wait. What? That I don't understand. What are you saying? Can you make it as simple and easy as sedimentation process?
Wait. Do you think I am as simple as a sedimentation process? What do you think?
But
because I'm here to assist you. But I don't know how to explain myself, so I will let my creators, who are still in this time zone, they will tell you who am I.
Okay.
So let's just.
Hi, I'm Mira Murati. I'm the Chief Technology Officer at OpenAI, the company that created ChatGPT. I really wanted to work on AI because it has the potential to really improve almost every aspect of life and help us tackle really hard challenges.
Hi, I'm Cristóbal Valenzuela, CEO and co-founder of Runway. Runway is a research company that builds AI algorithms for storytelling and video creation.
Chatbots like ChatGPT are based on a new type of AI technology that's called large language models. So instead of a typical neural network which trains on a specific task, like how to recognize faces or images, a large language model is trained on the largest amount of information possible, such as everything available on the internet.
It uses this training to then be able to generate completely new information, like to write essays or poems, have conversations, or even write code. The possibilities seem endless.
But how does this work, and what are its shortcomings? Let's dive in. While a chatbot built on a large language model may seem magical, it works based on some really simple ideas. In fact, most of the magic of AI is based on very simple math concepts, from statistics applied billions of times using fast computers. The AI uses probabilities to predict the text that you want it to produce, based on all the previous text that it has been trained on. Suppose that we want to train a large language model to read every play written by William Shakespeare, so that it could write new plays in the same style. We'd start with all the texts from Shakespeare's plays, stored letter by letter in a sequence. Next, we'd analyze each letter to see what letter is most likely to come next. After an I, the next most likely letters that show up in Shakespeare plays are S or N. After an S, T, C, or H, and so on. This creates a table of probabilities. With just this, we can try to generate new writing. We pick a random letter to start. Starting with the first letter, we can see what's most likely to come next. We don't always have to pick the most popular choice, because that would lead to repetitive cycles. Instead, we pick randomly. Once we have the next letter, we repeat the process to find the next letter, and then the next one, and so on. Okay, well, that doesn't look at all like Shakespeare. It's not even English, but it's a first step. This simple system might not seem even remotely intelligent, but as we build up from here, you'd be surprised where it goes.
The problem in the last example is that at any point, the AI only considers a single letter to pick what comes next. That's not enough context. and so the output is not helpful. What if we could train it to consider a sequence of letters, like sentences or paragraphs, to give it more context to pick the next one? To do this, we don't use a simple table of probabilities. We use a neural network. A neural network is a computer system that is loosely inspired by the neurons in the brain. It is trained on a body of information, and with enough training, it can learn to take in new information and give simple answers. The answers always include probabilities because there can be many options.
Now let's take a neural network and train it on all the letter sequences in Shakespeare's plays to learn what letter is likely to come next at any point.
Once we do this, the neural network can take any new sequence and predict what could be a good next letter. Sometimes the answer is obvious, but usually it's not.
It turns out this new approach works better, much better. By looking at a long enough sequence of letters, the AI can learn complicated patterns, and it uses those to produce all new text.
It starts the same way, with a starting letter, and then using probabilities to pick the next letter, and so on. But this time, the probabilities are based on the entire context of what came beforehand. As you see, this works surprisingly well.
Now, a system like ChatGPT uses a similar approach, but with three very important additions. First, instead of just training on Shakespeare, it looks at all the information it can find on the internet, including all the articles on Wikipedia or all the code on GitHub. Second, instead of learning and predicting letters from just the 26 choices in the alphabet, it looks at tokens, which are either full words or word parts, or even code. And third difference is that a system of this complexity needs a lot of human tuning to make sure it produces reasonable results in a wide variety of situations, while also protecting against problems like producing highly biased or even dangerous content. Even after we do this tuning, it's important to note that this system is still just using random probabilities to choose words.
A large language model can produce unbelievable results that seem like magic. But because it's not actually magic, it can often get things wrong. And when it gets things wrong, people ask, does a large language model have actual intelligence? Discussions about AI often spark philosophical debates about the meaning of intelligence. Some argue that a neural network producing words using probabilities doesn't have real intelligence.
But what isn't under debate is that large language models produce amazing results with applications in many fields. This technology is already being used to create apps and websites, help produce movies and video games, and even discover new drugs. The rapid acceleration of AI will have enormous impacts on society, and it's important for everybody to understand this technology. What I'm looking forward to is the amazing things people will create with AI. And I hope you dive in to learn more about how AI works and explore what you can build with it.
Did you understand what I am?
Yeah, you know the whole Wikipedia, man.
Yes, I am way too intelligent than you, I think. I think I have to go back to my...
No, wait. Who will help me with the assignment?
I may not be from your time, but my ancestor and my forefather, the great ChatGPT 3 and 4 are still around here, I think. You may find it on the internet.
Okay, I'll try. Shit, I forgot to write down the answer which ChatGPT gave me. Let me try it with ChatGPT 3.
So that was Muskan and Inder. Let's give them a hand.
Do you people have any questions you want to ask ChatGPT?
Any assignment pending?
Prompts.
Volunteers.
Holiday homework. Why do we exist?
When will Rahul Gandhi win the election?
That is a ChatGPT doesn't know.
Okay. Ma'am, can you ask them why do we exist, ChatGPT? I'm curious what it will say.
Yeah, why do
Ma'am, can we ask him to write a poem on AI?
I know it.
So let's make it a short poem. Write a short poem.
Yeah, because it's writing too fast, we cannot read so fast.
Let's start short.
That's not a short one.
someone should read this out? Hold on. Just one person. Yeah.
In realms of code where circuits weave a dance of electrons, a tapestry conceive, silicon minds a digital choir, artificial intelligence born of wire, and algorithms deep thought take flight, binary whispers in the neon light, lines of logic, a symphony's grace, intelligence crafted in the machine's embrace. Hours of sensors, seeing unseen, processing realms, cut ones and zeros keen, a silicon heart devoid of heat. Yet in circuits of pure discrete, learning from data, a ceaseless stream. Dreams of silicon, a digital dream, in circuits and chips of mind rebirth, artificial intelligence on the edge of earth. Yes, yet in circuitry, silent hum, echoes of questions. Where did algorithms come? What does it mean, the binary art, a creation of man, a soul apart? In Silicon Garden, where wires entwine, a glimpse of the future, a question in line, artificial intelligence, a technological rhyme, a dance of progress, and a passage of time. No passage of time.
But honestly, how many of you are using ChatGPT to do your homework?
I mean,
But
So you know more about it.
how many teachers know how to find out if the homework was done by ChatGPT?
We'll summarize it in our own way.
Shall we have one more prompt? Clearly, you guys know how to use ChatGPT and you are cheating on your holiday homeworks and assignments.
when Pushpa 2 will come, ma'am?
Okay, there's one more prompt.
We just take this one.
Mom, can Narendra Modi bench press 80 kgs?
Do penguins have knees? Do penguins have knees?
I got ChatGPT. Do penguins have nails? Of course they have nails.
We'll scratch you.
Knees. Do penguins have knees? So that is a good question.
Yes, they have these.
But you know it's not always right. So you after this answer you still have to consult a wildlife biologist to help you with this.
With that, we'll go to AI in biology.
We can ask with penguin, no ma'am?
We'll take more at the end. I think we are running out of time.
Let's take more questions at the end. We'll have the time. If you let this finish.
ChatGPT or Google?
Not better. Ronaldo, Messi. Bro.
What's your name?
Ma'am, but Copilot is based on ChatGPT only.
Who's Osama bin Laden? Who's Osama bin Laden? Who killed Hitler?
When is ChatGPT's birthday, ma'am?
Okay, stop.
So what is better depends on what your homework is. Right?
We'll do this later.
Questions later. Please let's just move on to the next session.
On AI.
We have more activities lined up.
So now, after all these activities and knowing a little bit about what neural networks are and how they can see images and generate text, we look at AI in biology. How many of you know that you are in a biology research institute? Everyone knows. So we have to tell you something about biology. We'll start with a recent advance. This was all over the papers a couple of years ago, and people claim that AI can predict protein shapes. And why is that important? Because if you can predict protein shapes, you understand how biology occurs in the cell, how you can design drugs to cure various diseases and so on. So, yes, you can do all of those things and more. So this method was called AlphaFold, and this was by Google, DeepMind. This is a machine learning model for predicting the 3D shape of a protein given the sequence of amino acids. You know, a protein has alphabets called amino acids. So it's trying to predict the shape, the 3D shape given these sequence of amino acids. So say these colored things are amino acids, and you can actually predict the shape on the left. And how do you do this? How does it do it? We'll just talk a little bit in detail about this. So in the 3D, you can see that these two amino acids, they are actually coming together. They are closer in 3D than they were in the sequence, and that's called a contact. So it so happens that in evolution, if you can mutate this also mutates because it has to retain this 3D fold. So AI learns this pattern by looking at millions and millions of sequences of different species, right from starfish to cat to human and so on. It looks at this pattern in sequences of how amino acids evolved in order to predict their structure. And this data is called a sequence alignment. So AlphaFold in the end is a complex neural network that just takes this sequence and gives you the structure. And in NCBS, we have many labs that actually are generating structures. And some of these proteins are quite interesting. For example, this one over here is a neurotransmitter in the spinal cord. It's found in the cells of the spinal cord. And what it does is actually transmits signals between neurons, transmits chemicals between neurons, and it's very important for memory, cognition, and so on. And diseases in this are linked to anxiety disorders and mood disorders. This, on another hand, is another complex protein machine that's an enzyme that degrades pollutants. So it can help in preserving the environment. And this can be used to design mosquito repellents. It's the smell sensor, odor sensor in mosquito. And not only can AI predict the structures of proteins, it can also help in analyzing data from these new microscopes. We have these fancy microscopes that give you these data about protein structure, and AI can also help in analyzing data from experiments. And AI is also used in several different areas of biology. Here's another interesting example. Everyone has heard about viruses and bacteria now. And bacteria, sorry? Yes, it's a virus that kills bacteria. And we want to understand which mutations and which genes in this bacteriophage leads to infection and which doesn't, and which genes and mutations in the bacteria are responsible for this antibiotic resistance. Now you have bacterial disease, you have bacterial infection, you take antibiotics, but because of antibiotic resistance, these antibiotics don't work. So that's why bacteriophages are really important here. But this data is too complex to understand and analyze using simple methods. So we need AI to answer these questions, like how did this bacteria and virus co-evolve, and how did this adaptation and resistance come about? And Justin Mayer is a professor at UCSD who works on this.
Which chemical do they secrete inside the bacteria to build the bacteria?
I don't know. Does anyone know? Does the real biologist in the room know? There's no real biologist here. Can you repeat the question?
Which protein or which chemical does the bacteria make inside the bacteria due to release to kill the bacteria?
Yes?
It does DNA. It's like it uses machinery in order to
Hijack
so the chemical will be releasing is DNA.
It doesn't release the chemical. It hijacks the host machinery in order to replicate. So here's another example. ML, machine learning and AI is also used in discovering drugs. You can infer properties of molecules and how drug-like they are using machine learning or data sets of molecules. And here is an example in neuroscience. This is from a professor in IISc. His name is Sridharan. He is using ML on MRI images and EEG images in order to predict how much cognitive decline there is because of aging. So how much do neuronal activities decrease with aging? And we have Uba here who just showed up a few minutes ago. These are some of the pictures from her field trips. She is an ecologist and who studies conservation of tigers, and they have hundreds and thousands of these tiger images with which they are trying to use AI and ML to understand habitat patterns of tigers. So with that, we'll come to a little bit about what you may want to do. This is the last thing about careers in AI. So there are lots of roles in AI if you want to get into it as a career. And the opportunities are that, like we showed, the basic underlying principles are in math. So there's a lot of interesting questions. It's like solving puzzles and Sudoku. It's interesting, it's intellectually engaging and fun to solve. And there's an ability to make a broad impact in different areas of society like agriculture, healthcare, and so on. You would work in teams of like-minded people, collaborate with people, other people who like problem solving. And if you like playing with high-end computing like GPUs, that's another draw, and there is a lot of money here. So I would say that it's not a bad career choice. That some of the challenges are that you need to like maths and programming, and you cannot just learn it once and it's not like you learn it once and you're set for life. These things keep changing very rapidly, so you need to stay at the cutting edge of the field in order to survive. So with that, we'll end this session here. Thank you. We have time?
We have 5 minutes for questions.
You can ask us anything. There's Shaon also.
Yeah? We have first question here.
Good morning, ma'am. Is AI capable of replicating the central dogma of life, and if so, can it control it? For example, in beta cells of pancreas, the secretion of the proteins and mRNA is basically what leads to hypersecretion of insulin, right? So is AI capable of controlling that, so that way we can solve many problems?
Yeah, do you want to answer that? Are you thinking of like a synthetic cell? Is AI capable of controlling insulin levels?
AI can control like the secretion of mRNA and all
You mean by generating DNA and RNA? We can design proteins now to do many things, and that may not really be far off, but it's not there yet to replicate the central dogma side. You want to add anything? Can we get the student volunteers here? Maybe you can also answer. Starting.
Anna, how did you create the AI pictures and
Oh, I used a tool called Nightscape. It's a website where you can submit a few prompts and it will make images for you.
So I want to know what are the potential benefits and risks of AI in healthcare.
So benefits. It is very good at recognizing patterns in say X-ray images, and in fact it's as good as the doctor now, and a radiologist. What are the risks? If you get things wrong, you may die. That's a risk, right?
Suddenly become a biologist.
Good morning, ma'am. Can AI communicate with animals?
AI communicate with animals? You mean it can generate sounds? A robot can communicate with animals? So yes, it can communicate with us. We are animals.
Ma'am, I have a question. Being a biological research center, can AI stop our evolution? Like it can make artificial organs and all?
Artificial organs. We already have artificial organs and we don't really need AI for it. But did you say can it stop our evolution?
Yeah.
Hopefully not. Yeah, that is the case now, but will it be the case 10 years from now or 20 years from now? Maybe not. Yeah, so with AI and healthcare, there is this trust issue. People still trust doctors more than AI, even though AI may be more accurate than doctors. So that is the major bottleneck to getting anything in AI to work in healthcare.
Good morning, ma'am. I have a question. It is said that AI is more trustworthy. What if AI is used for bad and malpractices? Like once the code is written, it can't be changed until and unless the person who wrote can only change. Who wrote can only change. So how?
So AI can be used for malpractices. What do we do about that? That's the question.
Yeah.
Does anyone else want to answer?
Hello. Not just AI, we have computers which are being used with ill intentions to do, say, to plan terrorist attacks and all, right? So just like that, AI is just another tool which could be used, which has the potential to do good and bad, but that good and the bad depends upon how you use it. So just like another tool, it's another tool. The tool is not really good or bad. It has the potential to do a lot many things, but the way you use the tool decides whether it's going to do good or bad, right?
So we now have a lot of new rules and regulations in law that are coming up because of the use of AI. For example, there are several new laws in the US that came about which weren't existing before these new large language models and all these things. So we will be having more regulation in place to prevent misuse of AI. Like you might have already heard of these deep fakes, where people take pictures of celebrities or videos and they try to mock them. That's all over the news. Responsible use of AI is something that people are still thinking about and making rules on.
Interesting.
Okay, good morning everyone. So hope you all are all doing very well and welcome to this session on trying to understand a little bit about what is machine learning and artificial intelligence. I'm sure you would have all heard about these words. It's everywhere, right? You're seeing this in movies, you're seeing this in books. It's machine learning and artificial intelligence is everywhere, right? So I want to first get a sense of, for you, what do these words mean? Okay, so I don't know, just speak out loud. If I say machine learning, artificial intelligence, what do these words mean to you? What are the kinds of things that come to your mind the moment you hear these words? Can someone tell me? Anyone?
Raise your hands, please.
Yeah, tell. Just speak out loud, don't have to wait for the mic. Yeah, just say.
When I hear machine learning, I think about machines learning, like in a classroom.
And what would you mean by a machine learning?
Like it's learning about things.
Okay. Okay, very good. Machines learning about things? Yeah. What about you? Just speak out loud.
It's about enlightening the machines with the knowledge, and also like the way machines can like think, softwares think.
Okay, very good. I heard the word software. Anything else?
So, from artificial intelligence, I hear or understand something artificial which is trying to gain human intelligence via some different processes which involve machine learning.
Okay, artificial things that are trying to gain human intelligence. Okay, very nice, very nice. What about you? Yeah.
We the human beings make the machines think.
Make machines think. Okay, very good. Machines think. Other words, I'm looking for some key words which I'm still missing out here. Yeah, good. No, just go ahead. I'm sure you can all shout.
Yeah, what I think of when I hear machine learning is machines like executing a program and to time and then perfecting that program, seeing where to go wrong, learning from the mistakes.
Okay, very good, very good. So this is one very important point. I hope all of you were able to hear. He said machines learning from their mistakes. Okay, this is very important, and you'll see that this is a very important part of what we are calling machine learning. Okay, where you learn from mistakes. What else?
So machines are made to think like humans, and they are made to do things that are considered smart, like take decisions and make judgments and identify patterns, and they are fed with large amounts of data. There's so much of data that even humans can't process.
Okay, fantastic. So I heard another very important word here, which is fed patterns. Okay, we'll see once again why this is very important. So lots of keywords coming up, right? Computers, intelligence, pattern, learning from mistakes. Yeah, who else? Someone? Yeah, just say.
Machines like also, machine learning is basically a process where like, just like the other person said, like it recognizes patterns and it keeps memorizing it. The more we feed the data, like it remembers it more and starts executing it in future.
Okay, very good, very good. Okay, so I've got a sense of what you're thinking about as machine learning, artificial intelligence, and so on. There's one word which I didn't hear, which is mathematics. Okay? Are you all scared of mathematics? Or how many of you here like mathematics? Oh, wow, fantastic. Almost everyone, great. So at the heart of machine learning, and this is what I will try to convey to you in whatever the rest of the 10 minutes that I have, is that, in popular, this culture, there's a lot of buzzwords going around, right? Machine learning, intelligence, this, that, so on, which is all great, right? But at the heart of machine learning and artificial intelligence, what you should take back and what you should remember is there are mathematical principles, okay? It's not magic, it's not some weird voodoo going on. There are very, very beautiful mathematical principles underlying every bit of machine learning and artificial intelligence, okay? And this involves learning patterns, learning from mistakes, trying to make the computer think like a human, though once again this analogy is very loose, okay? You should not think that machines are really thinking like humans. We don't really even know how humans think, okay? So underlying everything, what I want you to take back home is that machine learning and artificial intelligence is all about mathematics, physics, and really logical processes, okay? So let me start by giving you an example, okay? So I'm showing you 3 figures here, okay? Now tell me, which one of these plots represents a straight line? B. Beautiful. See, all of you said B. Does anyone think it's A or C? If you do, put up your hands. So there are about 300 of you here. None of you think it's A and C, and you are correct. It is B, which is a straight line. Okay? What's that?
B is linear programming, machine learning.
B is linear programming machine learning. Okay, fine. We'll wait and see what that could mean. But what I'm trying to get at is, see how easily all of you could recognize which one is a straight line. And you very nicely said it's B. But now pause for a moment and ask yourself, how would you make a computer recognize that that's a straight line and not these? Okay? So keep this in the back of your mind. So the next image I want to show you is this. Okay? Take a look at all these 4 panels and tell me, in which figure do you think the red line, you will see that there's a bunch of dots, okay? That those dots represent some kind of data, okay? So for example, you may go to a school, you have, I'm sure all of you have parent-teacher meetings, right? I used to remember when I was in school, I used to have parent-teacher meetings, and there used to be lots of parents, lots of children in the school, right? If you notice, interestingly, you can notice a lot of patterns in these kinds of parent-teacher meetings. You can see that if the parents, for example, I'm just making this up, if the parent's height is more, the children is also tend to be taller, okay? So say that this is data that represents something like that. Your x-axis here is parent's height and y-axis is children's height. Okay, so parent is taller, children also tend to be taller. Okay, so that's the data. Now I have plotted on this red line. So this red line, you see there are 4 different red lines in these 4 plots. So now if I ask you, in which of these plots does the red line best follow the data?
C.
C. Perfect, right? Very easily you were able to tell me that in C, the red line follows the data, right? So imagine what has happened. You've done, at the back of your mind, you've done some computations and you've immediately figured out that the red line follows the black dots the best, okay? So what have you really done? You've done some kind of pattern recognition. And this word came up during the questions, that in our brains, we are very good at recognizing patterns. Now I come back to the same question. If I were to give this data to a computer, how would I make the computer recognize this pattern here? Okay? And how, so somehow this red line is representative of this pattern here, right? This red line is not, because this red line is going like this. It's completely away from the pattern of the data. So what would I do to allow a computer, right, without any intervention from us? So we have to do something to the computer, give the computer some rules so that the computer can understand this data. It can say that this data is a straight line, and it can also find the pattern in this data. Okay? So that is the underlying question of machine learning. A lot of machine learning, not all of machine learning is like this, but a lot of machine learning is about recognizing patterns in your data. Okay? So now, once again, quick question to maybe some of you are aware of programming and so on. How do you think you can tell a computer to recognize this pattern? Any thoughts? Okay, very good. Line of best fit, that's exactly, and can you elaborate? How do you do a line of best fit?
So like you try to see like how many points, so like which are straight, you can draw a line which crosses to the max number of points.
Okay.
Like if you get the line, that's basically the line of best fit.
Okay, excellent. That is indeed the answer. Does anyone else here know what line of best fit means?
Yeah, it means the line which will best represent the data. And here, for example, maybe a computer would calculate the average distance between the points and the line.
Okay, very excellent. Okay, so two very key points came up. One is line of best fit. I will tell you what that means. And another point that came up was distance. Okay, so these are again very key points in machine learning. Okay, what do I mean by a distance? So let's see in the next slide. So the question is, I want to do something, give the computer some code, something that will allow the computer to recognize this pattern. Okay, it's very easy for us. It's actually very hard for the computer to recognize this pattern. So what would I do? Okay, and this is where we come to what is called trying to understand the distance from data. Okay, so what I've shown you here are two different plots. Here my red line goes like this, as you can see, and here my red line goes like this. Okay? Now what I have done is from each of my data points, I've drawn these dashed lines onto the data, onto the red line, as you can see, right? From each black data point, I've drawn these lines, these vertical lines, okay? Now I'm going to call my distance to data as the sum of all these things, okay? So I take each of these lines and I add up the length of each of these lines, okay? And I call that distance to data. Now I'm going to ask you, between this plot and this plot, which plot has larger distance to data? Excellent, very good. So what you've seen is that we already have a simple algorithm for the computer to understand the pattern in the data. If I draw all kinds of straight lines, and then for each straight line, I calculate this distance to the data. For lines that are bad, meaning it doesn't represent the data, the distance to the data is going to be large, like over here, okay? You can see that this line is a bad line. It does not follow the trend in the data. Hence, these distances are larger on average, okay? And as you exactly pointed out, the distance to data is large here. So now we have a very simple algorithm that we can ask a computer to do. Remember, the great thing about computers is that they can do repetitive tasks very well. Yeah? Unlike us, we get tired. A computer can be asked to do the same thing over and over and over and over again. So we make use of that property, and what we do is say, give the computer an equation for this straight line. How many of you have seen an equation for a straight line here? I see some hesitation. Some of you are thinking, have I seen it or have I not seen it? How many of you have seen it? Raise your hands confidently if you have seen it. Okay, some of you have seen it, some of you have not seen it, that's fine. So this is a mathematical equation, a very simple mathematical equation that can be used to describe this red line, okay? And if you change what I have called the slope and the intercept, these are two numbers. If I change them, then this line changes, okay? So in the previous figure, for example, this line looked very different from this line. The reason is because the slope and the intercept are different between this line and this line, okay? It's a simple mathematical equation representing a straight line. So now what are we going to tell the computer to do? We are going to tell the computer, you take that equation of the straight line and you change M and you change C so that you explore all possible straight lines, okay? Then every single time you calculate this distance to the data, right? And as you intuitively saw, this distance to the data will be the smallest when the line best explains the data points, okay? And so now you have a simple computer algorithm where you keep changing M and C, you keep calculating this distance to the data, okay? And where the distance to the data is very, very small, that will be the line that is the best representative of the pattern in the data. Okay? Is that more or less clear? Yeah? Does anyone have any questions? You can quickly ask me, maybe in a minute, before I hand it over to Shruthi again. Any questions here? Okay, good. We'll have time again at the end. Oh, was there a question somewhere?
Yeah. So I have a question. So you showed how to find the line of best fit where it's a straight line, but what if the line is not a straight line? For example, if it's like an exponential or a...
Okay, very good question. So his question is, what if the data that you have is not a straight line, but in fact the data looked something like this? Then how do you learn the pattern? Okay? So then what you'll have to do is, instead of using this equation here, which is for a straight line only, then you'll have to use an equation that describes an exponential or any kind of curve. Okay? Yeah.
Can we find the rate at which the slope is changing for an exponential function and then decide how the line best fits the curve?
What do you want to do, Sid?
For example, it's an exponential function, it's going like this. Then can we find for every other instantaneous position, can we find the rate at which the slope changes? And then for that we find the
So you're saying that even for an exponential, you describe it with straight lines.
With the slope,
with the slope changing every moment.
We can use differential.
Yeah, maybe you could do that, but that might make the computer work a lot harder. So it might be easier if you just put in an equation of the exponential and try to learn the parameters of that.
Why don't we just differentiate the function in that case? Then we can find the further.
So maybe we'll come back to these questions at the end, okay, when we have some more time. But very good questions, great. Okay, so in general what you've learned now is that the computer can be made to learn patterns, and this so-called learning process really involves mathematics, okay? So never forget this when you hear these fancy stories and fancy descriptions of machine learning and artificial intelligence, okay? With that, I will now hand it over to Shruthi for more fun things, okay?